Alrighty, let's talk transformations of power functions. And this is going to be our last lesson in our first unit. Before you get into this lesson, if you are unfamiliar or you need a bit of a refresher on graphing using step patterns, particularly parabolas, I'm going to strongly encourage you to pause this video and to just search up graphing parabolas with step patterns. That's going to help make things a lot smoother because I'm going to be using that same technique here today, and I don't want you to be totally lost. Let's just do a quick refresher here. This is a parabolic equation, or a quadratic equation, I should say, and there's a lot of different transformations that have been applied to it. We're just going to break them down one by one. The first transformation that I can see right at the end here is this is a vertical transformation. It is a shift down by 2. The -2 there is shifting things down by 2. We also have a horizontal shift that is happening. And it is headed to the left by 3, sorry, to the right. It's always the opposite when it is inside the bracket. So even though -3 looks like it would be going to the left, it's the opposite. It's actually going to the right. And you know what? I'm only going to highlight the number 3 because it's the opposite, of that sign. There we go. Then we've got a couple of stretches that are happening here. I'll do the first one out front. This one is actually a compression, I should say, because you're multiplying everything by 1/5. So this is a vertical compression by 1/5. The half is tricky. It is a little bit different because, again, it is on the inside of the function. And I know it's on the inside of the function because my function is squared. And the squared is being applied to everything within these square brackets. So when I say it's within the function, it's because the squared is on the outside of it. And so anytime you've got something within the function, it behaves in the opposite manner. Just like how with our 3, instead of going to the left, it actually went to the right. This is going to be the opposite as well. So it looks like it's going to be a compression, when in fact it's going to end up being a stretch. Because what's going to happen is I'm going to be dividing all of my x values by a half, which is the same thing as multiplying by 2, which is how we get up, or how it ends up being a stretch at the end of the day. And the very last transformation that we have here is, and I'll do it in pink, is this one. It is our negative at the very front. This is a reflection across the x-axis. So transformations for higher degree power functions. Remember, a parabola is just a power function. It's just got an exponent of 2. And we're going to be looking at cubic functions, which have an exponent of 3, quartic functions, which have an exponent of 4, and quintic functions, which have an exponent of 5. And everything works the exact same way in terms of the transformations. So we have our C at the end here. C continues to remain your vertical shift. D will remain your horizontal shift. A will be that vertical compression, or sorry, that vertical stretch. And K is going to be your horizontal, in this case, compression, until we know otherwise. And also recall that any reflection is built into the A value. So I'm just going to put a comma and I'm going to say reflection. I should say vertical reflection. And this is going to be the case for quite literally all power functions, so long as your power is an element of all real numbers. This totally works. Okay? So let's go through, we're going to graph a couple of examples here applying transformations. Some of you might be more comfortable from grade 10 and from grade 11 applying transformations using point mapping, which is where you create a table of values for your parent function, and then you apply all of the transformations mathematically and then plot the points. My hope is at the end of this lesson you recognize that simply using the transformations is going to work a lot smoother and a lot quicker than point mapping, and it also gives you a better visual understanding of the transformations. This is something that I'm certain is going to come up in the course again, and so point mapping may not be the best strategy for you today, so give it a shot if you haven't done it this way before. So let's look at our first example. We were asked to graph this cubic function, and it's specifically requesting for us to graph the parent function first. So that's what I'm going to do is I'm just going to create a quick table of values for my parent function. I like using these points because it includes the origin, which is often where that symmetry happens, especially for the parent function. And it gives us 5 good points. Our parent function is simply x cubed. So I'm going to cube all of these numbers to get my sort of initial values. -2 cubed is -8, and then it's -1, 0, 1, and 8. So I just cubed all of those numbers. And I'm going to go ahead and plot that on my grid to the right here. My y-axis is going up by 2s, my x-axis is going horizontally by half. There we go. And let's connect the dots and do our best to keep it smooth. All right, not bad. So that's our parent function. X cubed. You're always going to do your stretches before your shifts when you are doing your transformations. So let's go ahead and let's do the stretches first. The only stretch we have here is actually this vertical stretch by a factor of 2. So all of my points are going to be stretched vertically by a factor of 2. I'm just going to double all of them, truthfully, okay? And the only points that well, can I fit all of them? Let's see. Let's see what's going to happen here. So my 0, 0 is going to remain the same. That it can't be doubled. I had a point 1, 1. That's going to end up at 1, 2. Just like -1 will be now at -1, -2. My -8 will become a -16, and it'll be right there where my stretch takes place. All right, I'm going to go through and connect those dots. So hopefully you can see that that vertical stretch has been applied, and it's quite drastic. It's not so much up close, but I hope you can appreciate, especially as we're looking towards the tail end of our function here, how you can see how much steeper it is going to be happening. The next transformation that I'm going to apply is going to be my vertical flip, my vertical reflection, and truly all that's going to happen is I am going to flip my points. So I'll do this one in pink. The 0, 0 remains the same. This point will be flipped down. This will be flipped up. This guy comes up here, and that guy goes down here. So and we do our best to draw it nice and smooth. What's interesting here is that a vertical reflection also looks the same thing as a horizontal reflection. And last but not least, we have our shifts. I'm just going to do those in blue, and I'm going to do them simultaneously. So I have shifts that are happening. I'm going to go to the left by 3 and then down by 4. So I'm going to shift all of my points in that direction. Left by 3. So we'll go 1, 2, 3. Down by 4. Left by 3. 1, 2, 3. Down by 4. Left by 3, down by 4. 1, 2, 3. By 4. And then lastly, where are you? Here we go. 1, 2, 3. Down by 4. And I connect the dots. There we go. So the blue function is our final function. I'm going to label it with the equation. And I'll give it a highlight so it's easier to see. No, it's not. Never mind. Okay, so just to recap, we did our vertical stretch. We did our flip. And then we did our shift. Some people do flip first, and that's fine. Doesn't really make a difference. Now, a quick way to be graphing our cubic functions is we're going to take a look for a second at this point right here. So that point on our end function is sort of, I don't want to call it a turning point because it's not a turning point, but it's sort of a point in the middle that everything revolves around. I don't want to use the word vertex because it's not a vertex, but I hope you can see the significance of it. And I just want you to pay attention to where it's located. This was located at -3, -4, which ended up matching the transformations of the shifts, the horizontal shift and the vertical shift. So how convenient of it would it have been for me to simply just locate these shifts and immediately start by plotting that point there. That's actually how we're going to do a quote-unquote quick graph of our cubic function. So we're going to start at the starting point, okay, with our shortcut to graphing cubics. And I just want to make sure I'm using the right letters here. Our starting point is going to be at D, C, based on the transformations. Recall that D is your horizontal shift and C is going to be your vertical shift. And then we're going to follow in the same idea as the step pattern that we use for parabolas. And what the step pattern relies on is our first differences. So if we just take a look here for a quick sec, we'll do that color. The step from -8 to -1 is 7. Then it goes up by 1, then by 1 again, then by 7. And what that told us in terms of step pattern is that from our starting point, I went to the right, and then I would need to step vertically by this amount. So starting from our initial one, in this case, it would be 1. And what we actually ended up doing is we ended up multiplying these steps by the A value in order to figure out where our next step was going to be. So from the starting point, my first step, quote unquote, should be a 1, but in fact, I need to multiply it by -2. And so from here, I go to the right by 1, and I actually went down by 2. Just like for my other one, I went to the left by 1, and it would be the reverse. I went up by 2. My next step required 7, and I actually ended up going 14, and it was a -14 down. From my second point, I went to the right by 1, and then down by 14 to place the second point. So that technique is going to be the technique that we are going to use in order to do sort of a quick sketch of our step pattern, or sorry, of our cubic function. So our step pattern is going to be to the right by 1, up by 1, to the right by 1, up by 7. And if there are any transformations, we are going to need to multiply them. So for example, with our vertical, I'm going to need to multiply it by a. And for our horizontal, which is our x value here, I would need to divide by k. Remember, I need to do the opposite because it's inside the brackets. I'll do 2 more examples for you here, and feel free to pause if you'd like to do them on your own and then come back and check. Okay. I'm going to graph my first function here. My important point, my starting point, is located, let's write it down here, start at, and it's going to be located at 4, 1. Again, I got that from using these 2 numbers at the tail end here. So I'm going to plot my point 4, 1. And now I'm going to go ahead and do my step pattern. So step pattern should be up 1, right 1, up, sorry, that's totally backwards. Right 1, up 1, right 1, up 7. However, I do have an a value here. My a value is a half, so I actually need to multiply the y element of my step pattern by a half, in which case I'm going to be going up by a half and then up by 7 over 2, which is up by 3.5. So let's start at my starting point, and I'm going to add some new dots. I go to the right by 1, and then up by a half, so just right here. And then to the right by 1 again, and up by 7.5. So right by 1, this is a half, and so now I can go up 7. 1, nope. That's not true. 7 halves. 1, 2, 3, 4, 5, 6, 7. Perfect. Put a dot. Okay. My cubic function has point symmetry, although it is not an even function. And we know that it is going to look the same if I sort of take this section and rotate it 180 degrees down. So I can do sort of the opposite now to find 2 other points. I'm going to go to the left by 1 and down by a half. And then I'm going to go to the left by 1 again and down by 7 halves. 1, 2, 3, 4, 5, 6, 7. Just on the edge of the grid there. And we can go ahead and we can sketch. I add arrows to the end of my function to indicate that it does go on forever. And we are good. We've sketched our cubic function using the starting point and using that step pattern. Okay, let's do our second example here. Before we can proceed with our sort of starting point, recall that the interior of your function always needs to be in factored form, and currently it's not. If we were to ignore that, you would end up with the wrong starting point. So we do need to factor first. I'm just going to rewrite my function down here. And then I'm going to factor the interior. I can now locate my starting point, which is going to be at -2, +1. And so I can put my starting point there. Perfect. Now we need to determine our step pattern. You'll recall, once again, we were going up by 1, sorry, not up, right 1, up 1, right 1, up 7. But we need to transform these points. I'm going to do my vertical transformation first. I'm multiplying my y shifts there by -3. Which will give me that I'm actually going to be going down by 3 and then down by 21. And that's all coming from my -3 out front. And then I have a horizontal stretch as well that I need to consider. It is going to be, in fact, a compression because I need to be dividing everything by 3. So instead of going to the right by 1 every time, I'm going to be going to the right by 1/3 every time, which is going to be a little bit difficult to show on this graph, but I'll do my best. So I start at my starting point, I go to the right by 1/3, and I'm going to go down by 3. And that's where my first point is going to be. It's going to be near impossible. Actually, it is going to be impossible for me to put another point on my grid, so I'm just going to stop there. And I'll do up to the left instead. And it'll end up about here. And this is the tricky part. This is where we do our best to try and make this look like a cubic function and not like a straight line. A cubic function, recall, has this like nice sort of S shape in the middle. We do our best. There's some kind of squiggly going on there. We all get the idea. Okay. All right, let's look now at our quartic functions, or functions to the power of 4. Once again, we're starting off, we're being asked to graph this function that has a bunch of transformations, and we are first going to use our parent function. So I'm going to start by creating a handy table of values, just like I did last time, to graph my parent function. And I'm using the same x values. Recall that the parent function is x to the power of 4, so I'm going to put all of these to the power of 4. Really, the only thing that changes there is the 2 points, and I'll go ahead and plot them. -2 goes up to 16. Ooh, and how much is this graph going up by? Going up by 10s. So we're going to do our best to show it about there. Oh gosh. Almost 0, 0. Oh, no, above. And then 2 at 16. So it's sort of like a more square parabola because of how tight that bottom comes in. Oof. A bit of a wiggly end there. Okay, now let's graph those transformations. I'm going to start by doing my vertical stretch. I'm going to cut everything in half. Oh, good. Let's do it. Somehow, I'm going to cut these in half. They're going to go down a little bit further. 16 will drop down to 8, so it'll be about there. And then we will graph. Then I'm going to do my reflection out front there as well, and it's going to be flipped upside down. Actually, I'll do that guy in pink. all just doing our best. And then last but not least, I'm going to do my nice shift using the 7 and the 6. I'm going to go to the right by 7 and up by 6. Oh gosh. So I was at 0, 0. I should be up to 6 and then down to 5. If I can show that. Beautiful. And then my 2 was at 8. Oh gosh. So it's going to end up like here. We're all just doing our best. Oh, something like that. Something like that. So we can see once again that we are able to sort of shortcut this. It would have been a lot easier if I had just started at my starting point, which ended up being 7, 6. And then if I had simply just used my step pattern. So we're going to do the exact same thing. We started our vertex, which is located at, once again, at DC. And then we use our step pattern. Let's figure out what that pattern is. Well, this is 15 and then 1. So our step pattern usually is right 1, up 1, right 1, up 15. But recall that we have to transform that. So my verticals, I'm going to multiply by my A value, and the horizontal shifts I need to divide by the K value. There was no K value in this example, so I didn't have to show it. Okay, let's graph 2 examples using this shortcut now. I'm going to start with my first one here at my vertex, which is located at DC. So my vertex is at 1, -6. Right down here. Good. And now I'm going to use my step pattern. So instead of going to the, instead of up or right 1, up 1, right 1, up 15, I'm going to multiply that. There is no horizontal stretch here. There's no value in the K. So instead I'm going to just multiply both of these numbers by my A value to get to and 30. The 30 we won't be able to show on here, so we'll just do our best. I'm going to go to the right by 1, up by 2, put a point, and then do the same thing on the left, up by 2. This is going to end up looking like a parabola simply because of how zoomed in it is, but that's okay. It looks like an even degree, or sorry, it looks like it, yes, it looks like an even degree polynomial. That's what matters. Try the other way. My hand is all shaky today. There we go. And I add my arrows. Okay, we'll do the second one now. Once again, I start at my starting point, my vertex. This time is going to be located at -3, 4. Again, pulling from these two numbers here in the opposite of the one in the bracket. That's why it's a -3. I plot that point, -3 up to 4. Perfect. And now I need to be changing my step pattern. So right 1, up 1, right 1, up 15. Again, there's no horizontal stretch or compression here. There's no values, so these guys are good. However, I do need to transform my step pattern in the vertical direction by multiplying by negative 1 over 3. And my new steps are going to be actually going down by a third and then going down by 5. So I should be able to get both of them on this graph. Okay, right by 1, down by a third. Ooh, gotta zoom in for this. Ish. Hopefully that's there. And then right by 1, down by 5. So I'll end up about here. Ish, because that third is sort of hard to show. All right, now connect the dots to try and make some kind of, oh, that was not very good. We do our best. It looks like an even degree function. The second one here shows a little bit more of that like flat bottom parabola, which is what a quartic looks like, okay? And that's that. We get the idea. You can use this strategy for sort of quick graphing any power function. You've seen the pattern here. You start at the starting point, you figure out the step pattern, you apply the step pattern. Whether it's going to end up looking like some kind of an S shape with an odd degree function or some kind of U shape with an even degree function. That's it.